Hi everyone, today I'm going to go over one of the most important concepts in calculus, the derivative. Now, a derivative is just a really fancy word that means slope, and as you all know from algebra, the slope of a line is just the steepness of a line. In a linear equation, or an equation for a straight line, the slope is just a fraction indicating the rise over run, hence steepness. So in the infamous equation y equals mx plus b, the slope would be represented by m, where b would be the y-intercept, and the slope could be represented either as a constant or a fraction. If a fraction, say in y equals 2 over 3x plus 5, the slope would be 2/3, or it would be a vertical rise of 2 by a horizontal run of 3. Now, what if I had the equation y equals x squared plus 1, which had a graph of something to the effect of a parabola going to infinity? Now, does it even have a slope? I mean, the function is constantly changing, so how do we find the steepness of a function that's literally going all over the place? Well, there are two ways. There's a long way and then there's a shortcut. So let me go over the long way first. We can find the slope of an equation or a nonlinear equation by taking the limit of the difference quotient. And that's done by following the general long formula. The slope equals the limit as delta x approaches 0, and taking the difference quotient, which is f of x plus delta x minus f of x divided by delta x. Now, if you're not familiar with difference quotients, it's really important that you practice a few with easy equations until it becomes first nature. Difference quotients are on steroids in calculus, so it's really important that you understand the intuition of it. Basically, what we're trying to do here, using our previous example of y equals x squared plus 1, is just apply this difference quotient to the equation and then take the limit of it. So to do that, I am going to have to synthesize the difference quotient with my equation. And I do that by writing down my limit sign and going through all parts of the difference quotient. So as a crash course, what you do in a difference quotient is you pretty much replace whatever's in the parentheses here in this initial function with, or just pretty much plug it into x. So for every x in the equation, there's only one here, we would pretty much plug in whatever's inside the parentheses as such. So I would put in a bracket just so I can get more organized. I replace x with this, so x plus delta x, apply the square, and don't forget the 1. And in part 2, I just have to add my minus sign, and this is just telling me to rewrite this equation here. So that would be x squared plus 1, since f of x is just itself, all divided by delta x. Now comes the long tedious process of just simplifying everything. So I'm going to omit my limit for now, just for the sake of time. And what I want to do is I just want to expand this equation. So what I'm going to do is I'm going to take away the parentheses, or the brackets I should say, and just write everything out as it is. Now with everything all written out, I can continue simplifying it. What you want to do here is just FOIL it out, but for the sake of time I'll just tell you that that is x squared plus 2x times delta x plus delta x squared, don't forget the 1, minus x squared minus 1, all divided by delta x. Now, we can further simplify this by recognizing that these x squares pretty much subtract themselves out, and likewise these 1's. So what we have left here is 2x times delta x plus delta x squared, all divided by delta x. And we can further simplify this by pretty much just factoring out a delta x here, since we have 2. So that would condense down into delta x times 2x times delta x, all divided by delta x. And again, further simplifying, we can just cancel out these delta x's to the point where all we're left with is, again, bringing back my limit. It was there all throughout. I just pretty much withdrew it for the sake of saving some time. But the limit was there all throughout, and it's a good practice to just always write it out so you don't forget. And what we have here is just 2x plus delta x. Now I can't simplify that anymore, so I would take the limit of that, and to do so I would observe what constant delta x approaches. Here it's 0, and I would replace delta x, or anywhere I see a delta x, with a 0. So this is now technically 2x plus 0, which would really be 2x. And that is the slope, or the derivative, of y equals x squared plus 1. And that would be the long way of doing it.